Hello, welcome back to Unit 8. In the second part of Unit 8 here, we are going to divide our forces into conservative and non-conservative types. So what is a conservative force? A conservative force is a force such that the work done when you go from point A to point B is the same regardless of the path taken to get from A to B. Now, I'm going to use the three examples I did in part 1 as examples for this part 2. So I'm going to be pulling numbers that resulted in part 1 and using them here. So if you don't understand where they're coming from, go back and watch part 1. So let's consider the three forces we looked at in the last part. We looked at the gravitational force acting on a 3-kilogram object as we went from A to B along three paths, from A to O to B, from A to Q to B, and then along the diagonal directly from A to B. For the gravitational force, we found that for those three paths, the work along each path was the same. We then considered the force of friction along these same three paths. And we found that we could go from A to O to B or A to Q to B and get the same value. But if we went directly from A to B, the work was less because the distance from A to B along the hypotenuse, if you will, is less. Okay. Lastly, we picked a force that isn't anything other than this force. It was 16x in the I-hat direction plus 2xy in the j-hat direction. And for this one, we found that the amount of work done to get from A to B was completely different along all three paths. Okay. This means that the gravitational force would be conservative, again, only considering these three paths, whereas friction and my other one are non-conservative. Well, we checked three possible paths to get from A to B. Does that mean that gravity is going to be conservative along all paths? Well, there's a way to check that. So if a force is conservative, the work done by that force must be independent of path. This requires the work done to be an exact differential of the kinetic energy. So a little chunk of work has to equal a little change in kinetic energy. If our force can take the form of an x component in the x direction plus the y component in the y direction, then this exact differential will hold if df of x dy equals df of y dx. So now let's go check our three forces that we used as an example. So the first one I'm going to do is the force due to gravity. And for the force due to gravity, we found that it equaled mg in the negative j-hat direction. That doesn't look like a very good j. Let's try again. The negative j direction. And if I think about those two pieces, df of x dy will equal 0 because there is no f of x component. And df of y dx will also equal 0 because if I take a derivative of a constant, I get 0. Okay. Friction. We know the answer here is that friction is non-conservative. Okay, friction is like the most non-conservative force around. It would be the poster child for non-conservative forces. Using this criteria to find or to show this is really tough because in this case we had the magnitude of friction was constant, but the direction changed. Okay. And therefore, taking a derivative is not the greatest way to do it. So, again, friction is your poster child. It's a little hard to show with this criteria. Let's look at the last one that we had, though. So the last force was 16x I hat plus 2xy j hat. So if I take df of x dy, that would be d of 16x dy, and that equals 0 because there's no y dependence. And if I look at df of y dx, this one becomes d of 2xy dx, which equals 2y. And those two are definitely not the same, so we can say that this one is also going to be non-conservative. Okay. Again, friction is tricky, and I'm just going to put down here that this one's tricky to use this criteria to show. This concludes this part of Unit 8.